The human brain consists of billions of neurons with trillions of interconnections between them. The artificial neural networks are merely our efforts to computationally model the workings of our brain so that we can create intelligent machines. So let's start by looking at an individual neuron. So this is what a neuron looks like. At the center of this neuron is a nucleus. Surrounding it is the cell body called the soma. And this neuron receives stimulus or inputs from its environment through these dendrites. Amongst these many dendrites, there is one long protruding fiber called the axon, and this in turn has dendrites which can connect to other neurons. A neuron receives stimulus from other neurons through the dendrites, and if the stimulus is strong enough such that it exceeds given action potential, then the neuron fires and the output is relayed over the axon, which forms the input to some other neuron in the network. Through constant firing, the strength of the synaptic connection between the neurons strengthens over a period of time. So Hebb's rule states that if two neurons connected by a synapse fire simultaneously, then the synapses strengthens. And alternatively, if they do not fire simultaneously over a period of time, then the synapse weakens. In an essence, the synaptic connections represents the knowledge that has been learned by the network over a period of time. By itself, a neuron is a simple element and it does not do much other than fire electric pulses when it's sufficiently excited by stimulus from its neighbors. However, when you interconnect several neurons together in a massively parallel interconnected neural network, then you begin to see the simple interactions of these neurons lead to the emergence of higher level notions such as memory, thought, learning, and intelligence. There have been many efforts to computationally model the operations of a neuron, and by far one of the earliest and well-known efforts came from McClock and Pitts, and their model of neuron is perhaps one of the most widely studied. So the idea here is you have certain inputs which are representative of the dendrites, and these inputs arrive at a summing junction through weights W1, W2, Wn, etc. The weighted sum of inputs, let's call them H, is then passed on to an activation function which considers a threshold, and if the weighted sum of inputs is above this threshold, then the neuron fires and produces an output. Let's call this output Y. If the weighted sum of inputs is less than the threshold, then it does not produce any output. The computational model of the neuron is a simplification of the actual neuron it models. In particular, when you consider how the inputs are combined, they are simply linear sum of weighted sum of inputs that goes through an activation function. However, in reality, this process is non-linear. Also, in reality, when a neuron fires, there's a period of time for the neuron to recover or recoil. However, here in the computational model, there is no refractory period. The computational model of the neuron produces a simple output. However, in reality, it's not a singular output, it's more like a pulse train of spikes that is generated by neurons. And the other major difference is that you don't have a single unifying clock that gets all the neurons to fire at once. So in a human brain, you don't have a notion of a singular clock that coordinates the firing of all the neurons. However, a computational model that runs on a modern computer uses the system's clock to determine when the output should be produced. So all these simplifications make the computational model of a neuron deviate from the operations of an actual neuron. Having said that, it's just simply amazing that even with this level of simplification, the computational model of neuron is capable of learning concepts, as we will see. The weighted sum of inputs, let's label it capital X, is represented mathematically as sum of all weighted inputs xi wi. To this weighted sum of inputs, we apply an activation function that will cause the neuron to produce an output. Say we would like the neuron to fire when the weighted sum of inputs exceeds 0. So the activation function takes the form of a step function, which looks like this. So for all sum of inputs, weighted sum of inputs, if it's less than 0, the output produced by the neuron is 0, and as soon as it exceeds the threshold value of 0, the output produced by the activation function is 1. So this is the step response defined as. There are other activation functions that we can use instead. For instance, the sine function. So in a sine function, if the weighted sum of input is less than 0, then the neuron produces -1 as the output, and if it is greater than 0, then the neuron produces +1 response. Y and the x-axis is the weighted sum of inputs capital X. Unlike the step or the sine function, the sigmoid activation function is a continuous function. This function is defined by the expression y is equal to 1 over 1 plus e to the minus x, and the response curve looks something like this. In all these activation functions, the threshold is currently set to 0. What effect does the threshold have on the activation function? So let's say if I choose the threshold to be set to 1, the graph shifts to the right by 1 unit. So now the weighted sum of inputs need to be greater than 1 before the neuron fires. Now, instead of defining thresholds within the activation functions, as we have done here, we can introduce a bias input such that the weighted sum of inputs is automatically reduced by 1, and this produces the same effect as requiring the threshold of 1 before the neuron fires. So this is an alternative way of managing thresholds instead of explicitly stating it in the activation function. Given the model of a simple neuron, how do we get it to learn something? Let's say we would like the neuron to figure out how to perform a logical AND. So we have two inputs, x1 and x2, and the output, let's call the target output t, is here. So for two inputs, these are the possible combinations, and for logical AND, here are the target outputs that we would like the neuron to learn. Let's begin by randomly initializing the weights. So let's say W1 is set to 0.3, W2 is randomly chosen as minus 0.1. We pick a threshold, again, nothing special here. Let's say we picked 0.2 as the threshold. And for the activation function, we choose the step function. For the first line of training, if we applied the two inputs x1 0 and x2 as 0, the output that gets produced will be 0 times W1 plus 0 times W2. So this will be 0. And so given the threshold is set to 0.2, the output that is generated will be 0. So our neuron is producing the correct output. The target output was 0, and it indeed the actual output that's produced is also 0. So that's a job well done. Let's move on to the next line. With x1 set to 0 and x2 set to 1, the weighted sum of input is equal to negative 0.1, and since this is less than the threshold, the output again of the neuron is going to be 0, which is the correct answer. So it seems our initial estimates of the weights are quite good. Moving on to the next training line, with x1 set to 1 and x2 set to 0, the weighted sum of inputs that is received by the network is going to be 0.3, and this is of course greater than the threshold we set. Therefore the neuron is going to fire, and the output it produces is a 1. Now this does not go well with the training instances because we were expecting the target to be a 0. So there is a disagreement between what was expected out of the neuron and what it ended up producing. So how do we remedy this situation? Well, we adjust the weights such that the output produced by the neuron matches the target expected output. We can change the weights through trial and error fashion, but that's going to be a long, tedious process. What we need is a systematic way of changing the weights. And here we introduce the Perceptron training rule. The basic idea behind this training rule is to work out the error produced by the neuron, and this is defined as the difference between the target expected output and the actual output produced by the neuron. The next step is to adjust the individual weights. The new weight is equal to the old weight plus a small change in weight proportional to the error it's responsible for. The small change in weight is defined by the product of a constant called the learning rate, the error, and the ith input to that weight. Eta defines the learning rate, which is a small constant. In this case, we set it to 0.1. The idea behind using learning rates is that as we learn from new training instances, we do not want the knowledge accumulated from the prior instances to be lost. So this eta allows us to systematically change the weights such that we learn from the new examples without necessarily losing the old knowledge. Coming back to this example, let's see how are the weights adjusted for this particular set of inputs. So here the target output was 0, but the neuron produced 1. Therefore, the error is going to be -1. Weight 1 is going to be adjusted as follows. So the old value of W1 plus a small change in weight, which is defined by this expression here. So the learning rate is 0.1 multiplied by the error multiplied by the input to W1. So the input into W1 comes from X1, which is 1. Therefore, our new W1 becomes 0.2. Likewise, W2 is going to be the old W2 plus same learning rate. The error is -1 and the input to W2 comes from X2, which is 0. So here this equates to 0. There is no change to W2. An interesting observation is that if either the error is 0 or the input is 0, then there is no change in the weights. We go back and update the new weights. With the weights updated, we now move on to the next training instance. So the inputs are both 1. So 1 times the new W1 plus X2 times W2, we get 0.1, and here it is less than the threshold, and therefore the neuron produces an output of 0, which unfortunately is not the target output, and so here the error is going to be +1. And so with this new error, we'll have to work out the change in weights. I'll leave this as an exercise. The new weights you should get is W1 becomes 0.3 and W2 becomes 0. So this concludes one training epoch. And after this instance, we go back to the very first instance with the revised set of weights and keep training the network until the weights converge to a certain set of values whereby the error is reduced to 0 in all the training instances. So that's when we say that the neuron has learned to generalize this function. Let's pause for a while and ask ourselves, why does the perceptron rule work? Well, if you think about it, there are two possibilities. Suppose we have a very large output that is expected, but our perceptron is producing a small output. So in this case, the error is going to be positive. For the neuron to produce the expected output, what we need to do is to increase the weights. So you can see here, when the error is positive, the change in weight is also positive. Conversely, if the expected outcome is 0, but the neuron is producing a 1, we must reduce the weighted sum of inputs so that it does not exceed the threshold for it to produce the desired outcome. And in this case, that is achieved by reducing the weights, because the error here is going to be negative. So in this way, the error provides not only the magnitude of correction, but also the direction in which the weights should be adjusted. Continuing from the previous example, after a couple of training epochs, the weights are going to converge to 0.1, both W1 and W2. We can quickly check that the resulting weights indeed produce the desired outcome. Minus 0.2 is the threshold. So if you plug in any values of x1 and x2, you will find that for all these three combinations, the output will be less than 0. So therefore, the activation function yields a 0. And only in the last case, when you have x1 and x2 set to 1, then this is going to be 0.2 minus 0.2, which is 0. So we just meet the threshold of 0, and that's when the activation function produces a 1. The way we can visualize what the network is doing is to plot the two inputs, x1 and x2, and for each of the combination we look at the outputs. So when x1 is 0 and x2 is 0, the desired output should be a 0. When x1 is 1 but x2 is 0, the outcome n is 0. This point is 0 and 1, which is also a 0. When x1 is 1 and x2 is 1, then the desired output should be a 1. So what has happened is that our perceptron has learned to figure out the decision boundary which separates the two instances. So here is the boundary: anything less than 0, the activation function is going to produce a 0 output, and greater than equal to 0 yields a 1 from the activation function. So this is what the decision boundary looks like. Now suppose we would like our perceptron to learn the logical operation XOR. So given two variables, x1 and x2, the XOR function can be visualized as such. 0 XOR 0 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, and 1 XOR 1 is 0. So this presents a unique challenge to our perceptron, because you cannot possibly come up with a linear decision boundary that can separate the training instances nicely. So we say that this problem is linearly unseparable. The solution to this problem is to add more neurons to our network. So instead of a single perceptron, we can have two neurons, which takes two inputs as follows, and the outputs produced by these neurons goes into another neuron at the next layer, which then produces the final outcome y. So this will be able to solve the XOR problem. So as you increase the number of neurons and the number of layers of these neurons in your network, you're increasing the complexity of the decision boundary that can be learned to classify your data points. In summary, the neural network learns by adjusting the weights And in an essence, the knowledge that has been acquired is represented by these weights.